Gravitation. Introduction. We have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some force acting on the objects. The planets and the moon. Isaac Newton could grasp that the same force is responsible for all these. This force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. Objectives. Uniform circular motion. Universal law of gravitation. Free fall. Weight. Center of gravity. Uniform circular motion. Activity. Observing the motion of an object moving in a circular path. Take an electric motor and fix a disc to the shaft of the electric motor. Place a shallow wooden block on the disc at the edge as shown. Switch on the motor. Find the time required to complete 10 revolutions by the block and repeat the same 2 to 3 times. Begin counting the revolutions after few seconds of start of motor. The wooden block moves in a circular path with a constant speed. So, this motion of wooden block is called uniform circular motion. Uniform circular motion is a motion of the body with a constant speed in circular path. Activity. Drawing velocity vectors for a body in uniform circular motion. Draw the path of the wooden block and draw velocity vectors at successive time intervals as shown. Transfer tails of each velocity vector to coincide at a single point as shown. Without changing their directions, the directed line joining two vectors represents change in velocity. Let a body move with a constant speed v in a circular path of radius r. The velocity vector changes direction and appears to rotate. If a velocity vector is rotated through a small angle, the change in velocity will be represented by the base of the isosceles triangle as shown. Let us consider the change in velocity during the course of a complete revolution of a body. The sum of the magnitudes of the changes in velocity during a complete revolution will be equal to the sum of the sides of the depicted polygon, but the direction of velocity is changing continuously. It is perfectly clear that the smaller we take vertex angles of the small triangles, the lesser will be our error. The smaller the sides of our polygon, the closer they cling to the circles of the radius v as shown. Consequently, The exact value of the sum of the magnitudes of the changes in velocity of the body during the course of revolution will be equal to the circumference 2 pi v of the circle. We know that the magnitude of the acceleration is equal to the rotation of magnitude of change in velocity for one revolution and time period. Let AC be magnitude of acceleration of the body in uniform circular motion. That is, AC is equal to 2 pi v by t, where t is time required to complete revolution. We know that t is equal to 2 pi r by v. Substituting this expression in preceding formula, we get AC is equal to v square by r. As the vertex angle of isosceles triangles decreases, the angle between the change in velocity and velocity vector approaches 90 degrees. Therefore, the acceleration of a body in uniform circular motion is directed perpendicular to its velocity. But how are the velocity and acceleration directed relative to the path? Since the velocity is tangent to the path, the acceleration of the body is directed along the radius towards the center of the circle. The acceleration, which can change only the direction of velocity of a body, is called centripetal acceleration. Newton's second law says that net force on a moving body produces an acceleration in it, which is directed along the net force. So, in uniform circular motion, a net force acts towards the center. This net force is called centripetal force. The net force which can change only the direction of the velocity of a body is called centripetal force. Let us find the value of the centripetal force. According to the Newton's second law of motion, F net is equal to mass into acceleration. Fc is equal to mac. Fc is equal to mv square by r, since ac is equal to v square by r, where r is the radius of circle. In uniform circular motion, Fc always directs towards the center.